Welcome to our lecture. Our lecture is about relation between mathematical optimization and machine learning. We have collected some topics that are that constitute connection between these two topics. Our contents is as follows. We consider motivating example firstly in the area of optimization and also make some references. This after we start our main optimization problem and give some basic concepts, definitions, and such a formal framework for the mathematical optimization. And we make last remark about nonlinear convex optimization in the framework of optimization theory. Let me first introduce some historical remarks because mathematical optimization was firstly originated from the variational analysis, and variational analysis is a part of general functional analysis, a big area of mathematics, such that this was developed by many excellent colleagues from the mathematical science, and we make our optimization problem also in the abstract form. Of course, in the mathematical science, in applied mathematics, we have many classifications. And the first classification we do today is such division of the general mathematical optimization theory and consideration of the nonlinear optimization, generic structure of the modern optimization as a theory, numerical methods, and real-world applications. About real-world applications, it is a very good situation if a mathematical part of abstract theory make it possible to consider some real-world applications. And this was happened exactly with the mathematical optimization theory. It was converted to the engineering, to many engineering topics, and one of the most important topic today that is very related with the optimization theory is the machine learning. Here is our historical remark related to the big names in the mathematics that have contributed to the mathematical part of variational analysis and to the modern optimization theory. We also underline some professional areas of use of this big area, namely it can be used in every engineering area: electrical, electronic engineering, mechanical, telecommunication, of course automotive, and in energy. Also, financial engineering is absolutely has a very strong relation to the mathematical optimization. We speak about optimization of the financial markets, financial strategies, and so on. And of course, such a very complicated parts of engineering like aerospace, like management, and so on. Apart from that, we have also very strong basis for such very complex techniques like decision science, like behavior science, also operations research, and so on. And as mentioned above, we have very interesting relation to the modern machine learning and artificial intelligence. Let me mention some very interesting applications. For example, in robot dynamics, we need always to optimize trajectory, robot trajectory, and robot dynamics itself to make mission planning for robots such that the dynamic behavior of the robot will be optimal. And of course, this means that optimization constitutes a necessary tool for many modern or very modern engineering techniques. This fact also implies the existence of many professional societies that are dealing with classical optimization, with advanced optimization, with numerical methods, and with advanced numerical methods. I have indicated here some main professional societies. This is SIAM, Society of Industrial and Applied Mathematics, MOS, the biggest professional society, IEEE, is also very interested in optimization techniques, and many other society, International Federation Automatic Control, of course, some societies, professional society from economics, from financial science, management, and so on. This situation, of course, implies the existence of many special tools and softwares we have in our area, namely in theoretical and applied optimization. Let me mention here some optimization software we use, but this is only list of such usual optimization software. Only need to say that many companies, many big banks, many big industrial groups have proper software such that the development of these companies is independent on software that are common software. Under common software, I understand MATLAB optimization tool. You can see here some links. Very powerful Gurobi solver. Gurobi is a company that was many years ago a simple startup in the United States, and today this company is a leader of the common and advanced optimization software, also with relation to machine learning and artificial intelligence. In India and in many other countries, we have many Python users, and of course, the big possibility to use Python in optimization need also to be mentioned. We give here some link to the usual Python optimization page. And as last, we indicated here the Cplex. Cplex is one of the most oldest software in optimization developed by IBM Corporation. So that you can see many companies are very interested in optimization techniques because we have the corresponding software related to these big companies. For students and for advanced students, master, PhD, only can give some basic references. For example, Introduction to Nonlinear Optimization book written by SIAM, author Dept. And this is a really very nice introduction, the book number 1. The second book is a collection of algorithms that are presented in the book of MIT colleagues. The book number 3 is a very classical compendium, very big collection book related to the numerical method in optimization. The Jorge Nocedal is originally a Mexican colleague, but many years working in the United States. And book written by Rao, Engineering Optimization. This book gives very good insight into engineering part of the optimization theory, that means applications. We have to start with a simple example, and this is a very generic framework for optimization problem. We need to minimize a functional subject to some restrictions. And we are practically dealing with applied mathematics. Therefore, we have absolutely formal language used by mathematics, applied mathematics in the stage of problem formulation. We use absolutely abstract, formal, and mathematically rigorous formal method for formulation of the problem. We need to minimize the functional subject, in case of problem 1, subject to the inclusion and to some inequalities. Functional is given here as a specific partial functional only for this example, problem 1. And this is like possible formalization of the optimization problem in mechanical, in the particular part of mechanical engineering. We consider also unconstrained optimization. This is not obligatory such a practically oriented optimization framework. Why? Because we haven't constraints in this problem too. But in the real time, in the real life, we always have not only to optimize any functional, but also we have a huge presence of constraints. Let me note that in machine learning and in artificial intelligence, usually we have a huge dimensionality of many different restrictions, constraints. We call it constraints in our theory. Therefore, problem 2 can serve only as an academic example, only for starting of investigation or starting of learning in the sense of mathematical optimization theory. And let's consider such a very challenging classification in optimization given by the nature of our problems and our constraints. Namely, we can consider deterministic framework, we can frameworks in mathematics in general, but also with reflection to our problem statement and optimization. And my very important observation, we can consider static optimization. The example 1, 2, and this given example 3 constitute static optimization. But if we consider some real-time applications, our problems, specifically in engineering, are always moving in time and or living during a time, and therefore we need to incorporate for the adequate modeling framework aims some dynamical aspects in the problem formulation. And if we make this incorporation of time as a parameter, as a physical parameter into the optimization problem, we get dynamic optimization. Therefore, in fact, we present here very simple initial but very important classification. A problem of mathematical optimization can be static and deterministic, for example, static and stochastic, dynamic deterministic optimization, or dynamic stochastic optimization. Under these 4 classification possibilities, the most complex is dynamic stochastic optimization that incorporates also statistics and elements of probability theory. And of course, dynamic stochastic optimization has the most reflection and most connection to the machine learning if we think about reinforcement learning and stochastic models in machine learning. But we start with some basic problems, and in this sense, let's consider problem 4. This is a very generical, very classical formulation. We have 3 elements of the formulation. We have the objective functional given by j of x. We also consider minimization of this objective function in the sense of some restrictions, and the most general restrictions are given as inclusions. That means the variable belongs to subset of the vector space Rn. And let me repeat three main elements of the optimization problem. We have optimization value, optimization variable, in this case variable x. We have functional, we call it cost functional or objective functional, and we have restrictions given by some inclusions in the general case. Of course, we operated at the beginning with vectors and with matrices, with some subspaces of the final dimensional vector space, but we can also generalize this problem in the future. This is outside of the matter of our course, but it is possible to generalize this problem to infinite dimensional spaces and corresponding functionals and restrictions. If we do this formulation number 4, we can immediately consider some special cases. For example, special case if a subset A, calligraphic A, coincides with the full space Rn, and in this case, namely in this case, we get unconstrained optimization because our constraints coincides with the full space. If it is not the case, if we have really inclusion of calligraphic A in R, we get a constraint optimization problem that can be, as mentioned, static, dynamic, deterministic, or stochastic. Therefore, by this way, we get more details in classification. And let me note that classification plays a very important role at the beginning of every mathematical and at the beginning of every efficiently implementable theory. Then we observe that in some applications we need to maximize functional. For example, if we speak about financial or economical applications of the optimization theory, we need to maximize profit, gain, economical effect, and so on. But from the mathematical point of view, we can really stay on the basis of this optimization problem 4 that include minimization procedure. Why? Because we can redefine the functional and consider minus initial functional. In this case, we get minimization of the minus functional. Of course, is equivalent, mathematically equivalent to maximization. And some notation, every x that belongs to the set of restrictions is called admissible or feasible solution of our problem. In our case, or in, let me say, in the case of our course, but this case also constitutes a very important situation, our subset calligraphic A consists of some connected inequalities and equalities. If you speak about connection, we understand this connection in the sense of consideration of the system, interconnected system of inequalities and equalities. In the vector case, we can summarize this connection or this inequality as vector inequality and vector equality with the right hand side equal to 0. For example, we can give this admissibility set calligraphic A. For example 1, in this case we can define function g by such a way. And if we have very complicated problem, as problem 4 is not an elementary problem, the formulation is very easy, but the problem itself is very complex. And specifically, if we have high dimensional space or infinite dimensional space, or if we incorporate some element of stochastic or dynamics into the original problem 4. In this case, we get very complicated, sophisticated mathematical object, namely problem 4. And if we do that, we always get some additional questions about existency and uniqueness of the optimal solution. This is a pure mathematical formulation and very complicated, very sophisticated question about existency and about uniqueness of the solution of optimization problem. Therefore, in this situation, we need to apply also very powerful method of formal analysis of the modern functional analysis in order to solve this question of existency and uniqueness. But after that, we need to go by the algorithmic way, and this algorithmic approach is very natural for the modern AI and ML. And of course, generation or creating of very effective and efficient algorithms, solution techniques for optimization problem is the next part after establishing of existence of uniqueness, the next part of our possible research and also of our technical important question related to the right education in the sense of optimization theory. As usually, if the problem is really complex and with many possible sophisticated questions, we need to consider some special case. Consideration of special case in the situation of complicated mathematical behavior is an absolutely generic way to capture some phenomena that we can observe in the special cases, and then we have to be prepared, or we can be prepared to the more complicated phenomena in the case of general case. Therefore, we consider firstly such a convex and non-convex optimization. Let me note that this division in convex and non-convex optimization, this is the next possible classification. One can consider, that means one can consider, for example, dynamic stochastic problem that has convex or non-convex structure. In this case, we define, in parallel with this classification, we define the possible family of solution techniques. That means that our classification is not only such a mathematical tool that is usually applied to complicated problems, but also is very interesting or very important for right selection of the solution algorithm, solution approach. In order to understand what is convex or convex optimization problem, we need to introduce some very basic but such very nice and beautiful definitions from the convex analysis. Convex analysis is also a part of classical functional analysis, and here we are dealing with a definition of the convex functional. For convex functional, we define local minima here, and the local minima is given in definition. Local minima is considered on the neighborhood of the variable. We assume that the problem has an optimal solution. This solution is defined by x opt, and then in some neighborhood of this x opt, we define such inequality as a correct inequality, and in this case we speak about local solution. If we have local solution, we of course can introduce a global solution if we eliminate the neighborhood. In this case, we have the same inequality related to the x optimal, but this inequality is valid for full restriction area calligraphic A, for the full admissible set A. And of course, in the same case, we need to ask our theory about existence and non-existence of minima, because we have assumed that x optimal exists, but we haven't established the existence. We also can get multiply situation. In this case, we have multiplies minima or maxima, or we can also obtain many problems in which minima is unique. Convex optimization, as mentioned above, is strongly related to this local and global minima concept, and set, in this case our admissibility set calligraphic A, is given as a convex if and only if we have such inclusion for every convex combination for the two given points x1, x2 from the set of admissible solutions. That means if x3 combined as a convex combination of x1, x2 also belongs to calligraphic A, in this case the admissibility set calligraphic A is a set that we can call convex set. This after we introduce the convexity property not of the set, but convexity definition related to the functional. And of course, we think about our objective functional. If we speak about convex functional in general, one can consider a general definition, but in our case, we are related to the optimization problem. Therefore, our convexity of a functional is strongly related to the objective functional J. And this functional is called convex if we have such inequality, sometimes called Jensen inequality, but this is practically definition of the convexity of the functional. If functional J is convex, the functional constructed from the originally given with minus multiplication by minus will be concave, or reverse. If we have concave functional given as given originally, we can multiply with minus and obtain convex functional. After this, we are ready to give the general definition of convex optimization problem in the case of problem 4, and this definition selects a specific case of the problem 4, and in this case we can apply simple or relative simple solution procedure, theoretically simple as well as numerically simple. And we define convex optimization problem 4 as a problem in which we have convex functional J, but also convex admissible set A, calligraphic A. If both elements, objective functional and admissible set, are convex, then we have convex version of the problem 4. If we study any object, we need to collect some really simple property of this object, and of course we have spoken about convex set. Therefore, we give here some simple property of intersection of two convex set. Intersection is also convex, but union, for example, operation union is well known in the mathematics, but union of two convex sets is not obligatory convex. Also, only need to consider in dependence on the given problem some additional property of convex sets and convex functional. And useful property, or let me say the first because we are in introduction, the first useful property of the convex functionals. The sum of two convex functionals, G1 and G2, is a convex functional also, and also superposition is often a very useful mathematical operation if we have two functions, if we have two functionals. And of course, it is possible to ask if we have superposition of J1, J2, and both functionals are given as convex functionals. We obligatory get as a result a convex functional. The response is no, because we can get convex functional only in the case of some additional restrictions. For example, in the case if we have G2 as linear functional. That means the combination, the general combination of two convex functionals is not obligatory convex functional in the result, but one can select some important specific cases in which this superposition is a convex functional. This manner we start to investigate the important class of the nonlinear optimization problems called convex optimization problems. We have introduced the general definitions of solutions, local, global, and also some definitions of technical definitions and concepts of convex set and convex objective functional. And we have collected some simple initial properties of convex sets and convex functionals. We next use this all these concept definitions and also properties and also the general form of problem 4 given above for our development of the elements of the nonlinear optimization theory, and we do that in the next lectures. Many thanks. That's all. The lectures is completed.